An American wire gauge, or AWG, resistance chart provides information about the electrical resistance of different wire gauges, specifically when used as conduit. Electrical resistance is measured in ohms, and the chart typically lists the resistance per 1,000 feet of conduit for various AWG sizes. It is important to note that the resistance values provided are generally for copper conduit. Other materials, such as aluminum or steel, will have different resistance characteristics. To interpret the chart, first locate the specific AWG size of the conduit you are interested in. The chart will then provide the corresponding resistance value in ohms per 1,000 feet. This information is crucial for calculating voltage drop, determining the appropriate size of overcurrent protection devices, and ensuring the safe and efficient operation of electrical circuits. For example, a chart might show that 0 AWG conduit has a resistance of 0.117 ohms per 1,000 feet, while 24 AWG conduit has a resistance of 31.23 ohms per 1,000 feet. This significant difference in resistance highlights the importance of using the correct wire gauge for the intended application. Smaller gauge wires have higher resistance, which can lead to excessive voltage drop and potential overheating, especially over long distances. When using the AWG resistance chart, it is essential to consider the material of the conduit. Copper is a common choice due to its excellent conductivity, but other materials may be used in specific applications. If the conduit is made of a material other than copper, you will need to consult a different resistance chart that is specific to the material. The resistance of a conductor is determined by several factors. Firstly, the material of the conductor, with copper generally having lower resistance than aluminum. Secondly, the length of the conductor, as resistance increases proportionally with length. Thirdly, the cross-sectional area of the conductor. Larger conductors have lower resistance. And fourthly, the temperature of the conductor, as resistance typically increases with temperature. The AWG resistance chart provides a standardized way to compare the resistance of different wire gauges under specific conditions, typically at a standard temperature. The chart is a valuable tool for electricians, engineers, and anyone working with electrical systems. It helps to ensure that electrical circuits are properly designed and installed, minimizing the risk of electrical hazards and maximizing efficiency. To accurately use the AWG resistance chart, ensure that you are using a chart that corresponds to the correct conduit material. Also, consider any factors that may affect the resistance of the conductor, such as temperature variations. By carefully considering these factors, you can use the AWG resistance chart to make informed decisions about wire gauge selection and electrical circuit design. The information in an AWG resistance chart can be used to calculate the voltage drop in a circuit. Voltage drop is the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause electrical equipment to malfunction or operate inefficiently. To calculate voltage drop, multiply the current flowing through the conductor by the resistance of the conductor. The resistance can be obtained from the AWG resistance chart based on the wire gauge and length of the conductor. For example, if a 10 amp current is flowing through 500 feet of 12 AWG copper conduit, the voltage drop can be calculated as follows. From the AWG resistance chart, the resistance of 12 AWG copper conduit is 1.918 ohms per 1,000 feet. Therefore, the resistance of 500 feet of 12 AWG copper conduit is 1.918 ohms per 1,000 feet multiplied by 500 feet, which is equal to 0.959 ohms. The voltage drop is then 10 amps multiplied by 0.959 ohms, which is equal to 9.59 volts. This voltage drop should be within acceptable limits to ensure proper operation of the connected equipment. The AWG resistance chart can also be used to determine the appropriate size of overcurrent protection devices, such as circuit breakers or fuses. Overcurrent protection devices are designed to protect electrical circuits from damage caused by excessive current flow. The size of the overcurrent protection device must be chosen to protect the smallest gauge wire in the circuit. To determine the appropriate size of the overcurrent protection device, consult the National Electrical Code, or NEC. The NEC provides tables that specify the maximum allowable current for different wire gauges. The AWG resistance chart can be used to determine the wire gauge in a circuit, and the NEC tables can then be used to determine the appropriate size of the overcurrent protection device. For example, if a circuit contains 14 AWG copper conduit, the NEC table 310.15b16 indicates that the maximum allowable current for 14 AWG copper conduit is 15 amps. Therefore, the overcurrent protection device should be sized at 15 amps or less. Using an overcurrent protection device that is too large can allow excessive current to flow through the circuit, potentially causing overheating and fire. Understanding the AWG resistance chart is also important for understanding the concept of circular mills. Circular mil is a unit of area used to measure the cross-sectional area of a conductor. 1 circular mil is the area of a circle with a diameter of 0.1 inches. The AWG system is based on the circular mil area of the conductor. As the AWG number increases, the circular mil area of the conductor decreases, and the resistance of the conductor increases. The relationship between AWG number and circular mil area is not linear. Each decrease of 3 AWG numbers doubles the circular mil area, and each increase of 3 AWG numbers halves the circular mil area. For example, 10 AWG wire has approximately twice the circular mil area of 13 AWG wire. The circular mil area of a conductor is directly related to its current carrying capacity. A conductor with a larger circular mil area can carry more current without overheating. Therefore, when selecting a wire gauge for a specific application, it is important to consider both the current carrying capacity and the resistance of the conductor. The AWG resistance chart typically provides resistance values for direct current, or DC, circuits. For alternating current, or AC, circuits, the resistance may be slightly higher due to the skin effect. The skin effect is the tendency of alternating current to flow primarily near the surface of a conductor, reducing the effective cross-sectional area and increasing the resistance. The skin effect is more pronounced at higher frequencies. For most residential and commercial wiring applications, the skin effect is not a significant factor. However, for high-frequency applications such as radio frequency circuits, the skin effect must be taken into account when selecting a wire gauge. In addition to the AWG resistance chart, there are other factors to consider when selecting a wire gauge for a specific application. These factors include the ambient temperature, the type of insulation, and the installation method. High ambient temperatures can reduce the current carrying capacity of a conductor. The type of insulation also affects the current carrying capacity, as different insulation materials have different temperature ratings. The insulation method can also affect the current carrying capacity. For example, conductors that are installed in conduit may have a lower current carrying capacity than conductors that are installed in free air. It is important to consult the NEC and other applicable codes and standards to ensure that the selected wire gauge is appropriate for the specific application. The AWG resistance chart is a valuable tool for understanding the electrical characteristics of different wire gauges. By using the chart in conjunction with other relevant information, you can ensure that electrical circuits are properly designed and installed, minimizing the risk of electrical hazards and maximizing efficiency. Remember to always consult with a qualified electrician or electrical engineer for assistance with electrical projects. Working with electricity can be dangerous, and it is important to take all necessary safety precautions. Always to energize circuits before working on them, and use appropriate personal protective equipment such as gloves and safety glasses. By following these safety precautions, you can protect yourself from electrical shock and other hazards.